All right, so I'm going to be working through A1 2.4 EP2, which is our second little assignment on um, direct variation. Okay, so hopefully this will help you understand this. You could do it beforehand and check the key if you want, or you can work along with me as we're going through this. Okay. So Bernard Lavery, resident of the UK, has held several world records for growing giant vegetables. The graph shows the relationship between weight in kilograms and weight in pounds. Use the information in the graph to complete the table. So we've got the graph over here, and we want to complete the table. Okay, sounds good to me. All right, so let's look at the graph. So first of all, cabbage, kilograms, which is right here on the X value. And I think we lost our pounds over here, but that's the Y value. So cabbage is 56 pounds, which should be right around there, right? And then if we go up, I think coming over here, that's about, let's see here, 10, 20, 30, 40. These are by 10, so I'm gonna say 120 pounds. Okay, if I go to 108 kilograms, that's right around here, and I come over here, it looks like that's about 50 kilograms. Sorry, 108 pounds is 50 kilograms. Now 64 is about half of 120, so I'd expect this to be about half of 56. 64 kilograms is right around there, and it looks like I've got something maybe around here. 50, let's see, oh, is it 64? 64 pounds rather, and how many kilograms? It looks like that's about 25, 26, 20, maybe 27, let's say 27. Now this is 28, let's just say that this is 66, a little bit more. 21 kilograms, that's here. Looks like it's about maybe 48 or so. Now let's see here, 28 pounds over here, 20, let's see, 10, 20, 30, that's here. It's pretty hard to see, pretty small, but it looks like maybe around 15 kilograms. Now 9 kilograms is right about here, and I'm gonna guess that that is about 20 kilos. Then 18, let's say, is 7, why not? And 5, you know, let's say is, it looks like it's about 5. Okay. So that's probably not exactly right, but it's close enough. And we're just trying to estimate the points on these graphs. Okay, it says calculate the rate of pounds per kilogram. So that's going to be pounds divided by kilograms for each vegetable entry. So I need to do pounds divided by kilograms. So I'm going to do that. 120 divided by 56. So that is 2.14 pounds per kilo. If I do 108 divided by 50, I should get 2.16. If I do 64 divided by 27, I should get 2.37. Now I'm going to skip some of these and let you do that one, and that one. If I do 20 divided by 9, I get 2.22. If I do 18 divided by 7, I get 2.57. And if I do 5 divided by 5, I get, wait a second, 5 divided, this should be 10. I think I messed that up. That should be 10. I get 2. So it looks like it's right in this area. If I average some of these, so 2.37 plus 2.16 plus 2.14 plus 2.22 plus 2.57, I get that. Let's say, I don't know how many there was divided by 5. 2.2, seems like around 2.2, say 2.2 kilograms per pound, around that much. Okay, so that seems like the rate that I think best represents the data. So I'm just going to go through here and make sure I've answered everything. Calculate the rate of pounds per kilogram for each vegetable. Did that. Use the rate you think best represents the data as the constant of variation, 2.2. Write an equation to represent the relationship between pounds and kilograms. So pounds or kilogram, pounds is equal to 2.2 times kilograms. So that is my relationship to check my units, I'm going to write off the page here. I would have y pounds is equal to 2.2 wait, did I mix this up? This is pounds per kilogram. I messed this up. Oh dear. So that's why you check your units, so you can find your mistakes. This would be pounds per kilogram. Okay, pounds per kilogram. So this is pounds. Got to erase that again. So this is, again, pounds per kilogram times x kilograms. And so that ends up being pounds equals pounds. So y equals 2.2x. That's my equation like I had there. Okay, so this is a direct variation, which means that it passes through the point 0, 0, and it's the equation y equals 2.2x. Okay, great. All right, so I'm going to clear all this and then scroll down. Use the equation you wrote in 7b to find the weight in kilograms for a pumpkin that weighs 6.5 pounds. So remember, I've got y equals 2.2x. So remember that x is the number of, wait, is this right? Yeah, so y is pounds and x is kilos. So 6.5 pounds is a y value. So I'd get 6.5 is equal to 2.2 times x. Then to get x by itself, I can divide by 2.2. And that gives me x equals whatever 6.5 divided by 2.2 is, which is approximately 2.95 kilograms. So close to 3 kilograms. Use the equation you wrote to find the weight in pounds for an elephant that weighs 3,600 kilograms. So y equals 2.2x. Remember that x is kilograms and y is pounds. So since this is kilos, I can plug it in for x and get y equals 2.2 times 3,600, which should now be in pounds, 2.2 times 3,600, which is 7,920 kilograms. No, pounds rather. Okay. How many kilograms are in 100 pounds? How many pounds are in 100 kilograms? So 100 pounds, so that's x equals 100. We would have y equals 2.2 times 100. So that is 220. Nope, I messed that up. Whoopsie daisy. All right, so this is saying that y equals 100. This is saying that x equals 100. So 100 pounds times, we could do it this way if we wanted to, 1 kilogram, 2.2 pounds. So multiplying straight across, we'd basically just end up dividing by 2.2. So 100 divided by 2.2, which is about 45 kilograms. On the other hand, we could use our equation for y equals 2.2 times 100 and get 220 pounds is equal to 100 kilograms. So for the first part, it's 45 kilograms. And for the second part, it's 220 pounds. Okay, let's scroll down. Oh, that's it. All right, so hopefully that was helpful. I'll see you later.